Hello everyone. Today we're going to talk about linear regression, and I'm planning to do a video series on machine learning. So first of all, these slides that you see, these are actually from one of the courses that I did back during my master's, and these belong to Professor Alex Schwing. So huge credit to him for these, and this is my interpretation of these slides, so I hope I can explain it fairly well. So in this particular video, we are only going to talk about how we derive linear regression using the error view approach. We're going to talk about probabilistic approach of deriving linear regression in the next video. So first of all, the problem statement is fairly simple. We are given some data points, and these data points are given to us as tuples. So these are x comma y pairing that we have, and we're going to see this representation in the next slide. And our goal is to find a model which kind of fits these data points. So if we plot all these data points on a simple xy graph, then our job is to find a line or a model which kind of fits over these data points. Just writing it more mathematically, our linear model is a simple y equal to w1x plus w2, where w1 and w2 are parameters that we need to find out. And in this particular case, all the data points that we have, suppose say we have capital N as the number of data points, so we can create these pairings xi comma yi, and we need to find this y as a function of x. So that's why our model assumes that there is this linear relationship. And now we'll see how we can find the parameter values w1 and w2. The way we do it is fairly simple. Since we are given for every data point the yth value, which is the true value, so we subtract that true value from the predicted value of our model, which is given by w1 x of I minus w2. So here I is the I training sample, and or the I data point, and we sum the square of these errors over all the data points that we have. So we try to minimize this, and the thing that you see on the left, which is argmin, this just says that we are trying to find w1 and w2 so that the sum of all these squared errors that is minimized. So if you look this in the graph, then the line that you're trying to find out, that is just trying to be in such a way so that the total sum of all the green vertical lines that you see, the square of these is minimized. So here we can actually represent the above program that we saw in this vector notation. So we can stack up all the data points or all the outputs of the data points that you have as a column vector. So that is what you see in capital Y, which is an n cross 1 dimensional vector. And similarly, we can do it for capital X transpose. So this has all the x coordinate values for the n data points, and w1 and w2 are our parameters. So we can just simply differentiate this particular thing, and then we can find out the optimal w star, which is the optimal parameter that minimizes this total error that we have, and that simply is given as xx transpose inverse times xy. So if we plot this, we simply have a line that goes through all these data points, and we simply have our linear regression problem solved using the least squared errors approach. Now we can actually increase this to higher dimensional problems. So for instance, say what if data points that you had, the x actually belongs to a d dimensional space. And then we can talk about regularization and higher order polynomials. So for instance, like in this particular case, again, the output is still a real number, but the input to the model, that can be, say, of more than one dimension. So it could be like, say, d could be 2. So we could have for every data point there are these two parameters, x1 and x2, and we are trying to find y is equal to function of x1 comma x2. So our model is going to be yi is written as w naught plus summation from k equal to 1 to d of xki times wk. So this can be thought of as w naught plus w1 x1i plus w2 x2i plus w3 x3i and so on till the dth dimension. And then again you can represent this in the vector notation, and we can simply minimize the error, and the solution still remains the same. So w star solution can be found out. And suppose, say, like in this particular example, if our data points are given to us as shown on the left side, where we are trying to find y is equal to function of x1 comma x2, then in this particular approach, linear regression, we get this particular model which fits our data points. Now the next question that we have is, what if the number of data points are less than the dimension of the x vector plus 1, so n is less than d plus 1. If that happens, then the solution that we saw, this doesn't exist because the inverse won't exist. So in order to prevent that, we introduce this term c by 2 norm w square, where c is a constant and is greater than 0. So that's a parameter value that's in our hands. Then we get the solution as xx transpose plus c times I inverse times xy. And since c is greater than 0 and I is the identity matrix, this inverse will always exist. So we can always find w star, our parameters. Another thing to note here is that, suppose, say, if you make c very large, then the error that you're trying to minimize, that's going to be dominated by c by 2 times norm w square. So weight parameter values will become smaller as capital C value is higher. So that way you can ensure that your parameter values don't become too large. Now the second thing that I want to talk about is, suppose, say, instead of just making a linear model, what if I want to use a higher order polynomial instead? So in this particular case, suppose, say, I want to use 3 parameters now. What we have is that our model, which predicts yi, that's given by w2 times xi square plus w1 xi plus w0. So previously we saw that there were only 2 parameters, but now we have 3 parameters, and the dependence on x is now quadratic. In this particular case, I just want to mention that xi and yi both belonging to simple single dimension, and again we can just write the program in a very similar fashion. And here you can clearly see like why that vector notation helps us, because this is just a simple extrapolation of the case that we saw earlier. So all the data points y, they are stacked up in a column vector, x, they are stacked up in this phi transpose matrix, and all the w parameters are stacked in the w column vector, and the solution still becomes the same. So here phi is also called the feature vector or the feature matrix. We can clearly see that this phi is very similar to capital X that we saw earlier. We can see that if we plot both the models, that is, like if, say, the first model, which was yi is w1 xi plus w0 versus yi is w2 xi square plus w1 xi plus w0, then we can see that the model or the graph that is shown by them is very different. In case, like, say, if we want to fit all the data points onto the graph, then probably we might be interested in using a higher order polynomial representation. But in case, say, like if we are just want to find a trend or how data points are gonna shape up, then probably we might use a simpler model like a linear fitting or a linear model. So in this particular slide, I just want to sum up. We just saw this error view, and this is called the least squared errors approach. And in the next particular video, I'm going to talk about the probabilistic view and how we can derive the exact same model using probability. So thanks for watching, and if you have any questions or comments, please feel free to leave them below. Thank you.